Okay, good morning, good evening, good night, good afternoon, depending on when you're watching this. This video is going to be a walkthrough of the second lecture set for Stat 151. In this video, we will cover the first, sorry, should have been more prepared there. We will cover the first 47 slides, just talking about some key aspects of descriptive statistics. So for example, we are going to define variable types. We're going to talk about how to organize data. We're going to talk about how to describe data set via the concept of distribution. We will discuss measures of center and spread. And then we will also discuss visualizations like box plots and a little bit later on scatter plots. Okay, and then I'm just now realizing that a few of these slide number references are not quite correct, so I'll fix those up afterwards. All right, in lecture set number 1, we discussed two definitions of statistics. We actually talked about a lot of different definitions of statistics, but two of the distinctions or two definitions that I emphasize we should be able to distinguish between are descriptive and inferential statistics. In lecture set number 2, we're going to focus on descriptive statistics. So effectively, what descriptive statistics are tools that allow us to summarize the information in a data set. Now, there are many different types of descriptive statistics, and the ones that we use actually depend on the type of data that we are working with. To define the type of data that we are working with, we are first going to define variable types. But those definitions of variables are analogous to the definitions of data, as you will see in a little bit. Okay, so generally speaking, there are two types of variables, quantitative variables and qualitative variables. Quantitative variables are simply numbers or values. Qualitative variables are labels or categories. Like, for example, a data set that has an apple, an orange, and a pear in it would be qualitative. Um, a data set that has 6 numbers in it would be quantitative. Quantitative variables can be either discrete or continuous. Qualitative variables can be either non-ordinal or ordinal. Differentiating between the types of quantitative and qualitative variables is actually not that difficult. For example, a discrete quantitative variable is simply a value that appears as a whole number in the data set. So something like a count. For example, the number of laptops that are present in a classroom at any given time at the university. So in classroom number 1, there might be 7 laptops. In classroom number 2, there might be 12 laptops. In classroom number 3, there might be 16 laptops. For example, that is a discrete quantitative value because it appears as a whole number. A continuous quantitative value is one that is usually measured to some decimal point of accuracy, or it can be measured to some decimal point of accuracy. There is some subjectivity with this. For example, time can appear to be discrete quantitative. So for example, if you measure something to just whole number seconds, that would appear to be discrete. But time can also be measured very precisely to an infinite number of decimal places, if you will. And in that context, it could also be considered continuous. But in general, we distinguish between the two types based off of the presence or absence of a decimal space. So something that's a whole number is typically discrete, though again, there is a little bit of subjectivity there depending on what you're measuring. And something that has a decimal place or decimal places of accuracy is usually considered continuous. With qualitative variables, we have ordinal or non-ordinal. This distinction is also fairly straightforward. An ordinal qualitative variable is one that has an inherent order to it, hence the word ordinal, whereas a non-ordinal qualitative variable is simply one that has no understandable order. So for example, I had described a data set that had an apple, an orange, and a pear in it. That would be non-ordinal because there's no defined order between those three types of fruit. The apple doesn't necessarily come before the orange that comes before the pear. There's no natural ordering of those objects. An ordinal example might be something like month of the year, January, February, March, April, May, June, etc. We understand January to be the first month of the year, December to be the last month of the year. So if I'm working with a data set that considers month of the year, that has a predefined order, hence ordinal. All right, data. So the variable is simply what we are measuring. Now, when we start to collect values on the variable, we form data. So let's say, for example, I'm conducting a study where I'm going to measure someone's height, how many siblings they have, their eye color, and their gender. Height can be considered to be continuous quantitative. The number of siblings could be considered to be discrete quantitative, which would actually be the only way of defining it. Number of siblings is typically a whole number value. So I have two sisters or one brother or three siblings. Um, Height is one of those ones that sort of floats the line, I would say. You can measure height to just the number of inches, or you can get very precise with the value. It's so many inches, and then consider centimeters after that if you want to be very, very precise. Eye color is not an ordinal qualitative because there's no natural ordering to the colors, right? So my eyes are brown, or my eyes are blue, or my eyes are green. It doesn't matter what color they are. They those colors have no predefined order. And then the last one, oh, there's a typo here. So the last one would be rating of the class. So this could be um, a letter rating in this context. Right? So I rate this class as an A or a B or a C, like a letter grade. And in that context, there would be a predefined order. So we're getting a qualitative value out, A, B, C, D, for example. But A is understood to be better than B, is understood to be better than C, which is understood to be better than D. So there's a predefined order there. Okay, now let's say that effectively all we do is we collect multiple values on each one of these variables. So instead of just taking one student's height, I take the height of 10 students. And then I count how many siblings 10 students have. And then I record the eye color of 10 students. And then I get a rating from each of the 10 students. Now what I have done is form data. So data is simply a collection of values on each of the variables. Okay, so for example, here we have a qualitative data set. So this data set gives the final grades for an introductory statistics class. In this data set, we have 53 values. Okay, so here we have 53 observations. And as mentioned before, we have a qualitative ordinal variable or data. You can think of this either way. Again, these definitions of variable and data are really interchangeable in my opinion because we very rarely work with a data set that only has one value. In fact, we would almost never do that because we can't make any meaningful calculations or produce any meaningful summaries off only one value. So whether you want to describe the variable as being qualitative ordinal or the data as being qualitative ordinal in this particular case, it doesn't matter because you're describing the same thing. Okay, so we have, as I had said, 53 observations, so 53 different letter grades, and we are measuring a qualitative ordinal variable. And it's ordinal again because we understand A plus to be a highest score, followed by A, followed by A minus, followed by B plus, etc. So there's an established order to the letter grades. That's what makes this ordinal, and they are not numeric, which is what makes it qualitative. Now, the purpose of descriptive statistics is to organize the data. So we had 53 observations, which are shown here. And in this format, it's not overly meaningful to us. We can see, for example, there are some A's, there are some F's, there are some A pluses, there are some C minuses, just at a glance. But we would like to have a better description of this data. We would like to be able to summarize the information in a way that is easy to communicate and easy to digest. With qualitative data, the first thing that we would typically do is organize the information by counting how many of each occurrence we have. So this is done through what is called a frequency or relative frequency distribution. And in general, these distributions are actually quite easy to construct. The first thing we do is we identify the unique outcomes in the dataset, so the unique grades. So in this particular dataset, we have A plus, A minus, B plus, B minus, C plus, C minus. Notice there are no C's. A D plus, a D, and an F. So those are just the unique outcomes that are available to us. The second thing we do is we simply count how many of each of those we have. Now, you'll notice here that I have a tally column, which is a literal column where I have counted individually each of the occurrences. You don't have to do this. The frequency distribution is simply the count, right? So frequency and count are interchangeable in this context. So for example, I have 3 A pluses in the dataset. I have 8 A's in the dataset, 11 A minuses in the dataset, 6 B pluses in the dataset, 4 B's, etc. So the frequency distribution is a distribution of counts. How many times did each of the occurrences appear in the dataset? The relative frequency is simply the proportion of times that each of the outcomes appeared. And these proportions are found by taking the frequency and dividing it by the total, right? So for example, you can see the relative frequency or the proportion of A pluses in the data set is 0.06. That's 3 over 53. The proportion of A's is 8 over 53, which is 0.15. The proportion of A minuses is 11 over 53, which is 0.21. Okay, so the relative frequency is simply the proportion, and that's found by taking frequency and dividing by total number of observations. In the last column, I have the percentages. This is simply relative frequency multiplied by 100. So I've taken the proportion and multiplied by 100 here to get the percentages. So the relative frequency and the percentage distributions actually communicate the exact same thing. It's just that typically we are more used to dealing with percentages. It's more common for someone to say 6% of this data set had, or 6% of the students in this data set scored an A plus. 15% of the students in this data set scored an A, rather than 0.06 of the students scored an A plus, 0.15 of the students scored an A. The percentage is just easier to communicate, but it's a very simple calculation to determine a percentage from a relative frequency. Okay, so this is our first layer of summarization, the construction of a frequency relative frequency distribution. The second most common practice for qualitative data is then to construct a chart. So for qualitative data, there are two charts that are typically used. There are other options, but these are the most common ones, the pie chart and the bar chart. These are probably charts that you have seen in the past, but if not, I have examples coming up momentarily. Very simply, the pie chart is a literal circle, so a pie, and the pie is sliced into an area that corresponds to each of the number of unique outcomes. So you have different size slices of the pie that correspond to the relative frequencies or the percentages. The bar chart is simply a XY chart where on the x-axis you have unique outcomes, and on the y-axis you have the relative frequency, the percentage, or the frequency for the distribution. So the pie charts only communicate relative frequency or percentage, whereas a bar chart can communicate all three of the distributional information. So the frequency, the relative frequency, or the percentage. So for this data set, we have the following pie chart for percentage. You can see the pie chart is sliced into 11 unique outcomes corresponding to what was in our relative frequency and percentage distribution. And in this case, I labeled the pie charts using percentages. But you could also label the pie chart using the relative frequencies. It would look exactly the same. You would just be changing the value beside each of the outcomes. The bar chart is presented next to the pie chart. Again, you have an outcome for each unique letter grade. and the height of the bar is at the relative frequency in this case for each of the outcomes. Now, with the bar chart, you can change the y-axis to be frequency or to be percentage. And what's interesting is that the visualization itself, so the height of the bars and their proportion to one another, would never change. It would just be the axis values that you were changing. So you're really communicating the same thing regardless of which of the distributions you use. So regardless of whether you use frequency, relative frequency, or percentage, you're going to effectively produce the exact same image and have the same visualization of the relationship between the outcomes. Okay, so for qualitative data, regardless of whether it's ordinal or non-ordinal, our first step is usually to produce the summarizing distribution, frequency, relative frequency, or percentage, or some combination. The second step is to visualize. And in this context, when we want to visualize, we would use a pie chart or a bar chart. Those are the ones that are designed for qualitative data. Now, with quantitative data, we have quite a few more options that depend on the type of quantitative data we are working with and a few other considerations that have to be made even after the type. When we want to organize quantitative data, we want to use the same approach that we had just observed for qualitative data. So we start in the same place. We want to basically build a relative frequency or a percentage distribution. And then we want to place the observations into categories such that we can have that same kind of the same counts and the same percentages that we had observed for the qualitative data. Now, in order to do this, we have to either we have to bin, as we call it, the observations. And this can be done in three different ways. So there are three different binning strategies that can be used, and those depend on the type of quantitative data you're working with and then the characteristics of those particular quantitative values. Okay, so for example, one way of binning is to use what is called single value grouping. Now, single value grouping is used when we have discrete quantitative data, okay? But in this case, we have a low number of unique values with high repetition. Okay, so what I'm saying here is if we have a discrete quantitative data set, one binning option is single value grouping. We use single value grouping when we have a small number of unique values. So you can see here there's only 3 unique values, 3, 4, 5, and there's a high amount of repetition at each of those values. So we have 3 outcomes in the data set, 3, 4, 5. They are clearly discrete because they are whole number counts. We're counting the number of gears in a car. So cars typically only have whole number of gears. Like you can have 6 gears in a car, 5 gears in a car, etc. So a low number of unique values, but a lot of repetition at each value. So for example, we have 15 cars with 3 gears, 4 cars with 12 gears, 5 cars with 5 gears. So you can see that once we establish the binning or the grouping method, the rest of this is exactly the same as it was for qualitative data. So we have 15 3-gear cars. That's the frequency. Then we can convert frequency to relative frequency by taking each of the counts and dividing by the total number of cars. So for example, 15 over 32 is 0.46875. And then we can convert that to a percentage, which in this case would be 46.88, rounding off to the second decimal place. Right, so it's the same strategy that we looked at with qualitative data, and actually the single value grouping is the most similar to the qualitative data example. It's just deciding what grouping method you need to use. So for discrete quantitative data, we have single value grouping as an option. The second option is what is called limit grouping. Limit grouping, again, is for discrete quantitative data. But the difference here is that we have a high number of unique values and low repetition. So this is the somewhat opposing case. So we have high number of unique values, and we have low repetition. And I'm going to summarize these later as well. So there is a slide that explains the differences. But again, the point is for discrete quantitative data, we have two ways of binning, single value grouping and limit grouping. And it's entirely dependent on how much repetition you have and how many unique values you have. Again, there's some subjectivity here. There always is when you're picking these types of methods. But in most cases, it'll be fairly clear what approach is going to work best. Okay, now this is our first method of actually constructing a bin. So a bin, like you can think of in the literal context, it's like a box that you're going to place values into, and you have to establish the limits of the box. So the limit grouping method says take a particular value, define that as the lower limit, take an upper value, define it as the upper limit, and anything that sits between those limits goes into that box. So for example, here we have a discrete quantitative data set that has a high number of unique values and low repetition at each value. So this is an illustration that we would want to use limit grouping for. Now, you can see here the data is not ordered, but we choose the lowest possible limit to be 45. Okay, and we choose the highest limit to be 89. Sorry, I'll write highest limit. Okay, and this would be lowest limit. And then what we're doing is we're simply moving up by values of 5. Again, somewhat arbitrary, like you can do values of 10, for example, or maybe values of 3 if you wanted to. It depends on the data set, it depends on the number of values, and it depends on how far, like how spread out the values are from one another. In this particular illustration, bins of size 5 work well. So my first bin goes from 45 to 49. So any value that sits between 45 and 49 inclusive, we get placed into that bin. So you can see here that there's one bin or one value that sits in the first bin, and that's value 46. So 46 gets placed into the first bin. The second bin goes from 50 to 54. Again, these bins all have the same size. So 45, 46, 47, 48, 49 is size 5. 50, 51, 52, 53, 54 is size 5. And here we have three values that get placed in, 54, 51, and 53. Notice, again, we're taking values that sit on the limit. So I have an observation value of 54. That gets placed into this bin. So we're being inclusive of the limits in this particular example. Once we have counted how many observations are within each bin, then it's the same process that we've seen in the last two illustrations. We can compute relative frequencies by dividing by the total number of observations, and then we can convert the relative frequencies to percentages. So the actual organization across the examples that we have looked at is the same. Compute frequency, relative frequency, percentage distribution. What's changing is just how we group the values. So we can use the actual outcomes from the data set, or we can construct bins. Okay, the last grouping method is called Cutpoint grouping. So Cutpoint grouping is typically a value or a method that's used for continuous quantitative data. So data points that have decimal places of accuracy. Okay, so for example, here I have 22 observations. These are measuring time in minutes to 2 decimal places of accuracy. So this is clearly continuous. And we want to do the same thing. We want to construct a frequency, a relative frequency, and then a percent distribution. So how do we do this? Well, in this case, what we do is we effectively build limits exactly like we did before, but the structure of the limits is slightly different in interpretation than what they were in the previous illustration. So you'll notice, for example, here I have 1.5 to under 2. So this is basically saying I'm going to take a value of 1.5 or higher all the way up to 2, but not including 2. Right? So other interpretations of this, for example, could be 1.5 Just gonna make sure I have my bracket notation right. I'm pretty sure it's a square bracket. Yeah. So another notation of this could be 1.5 comma 2. Okay, so here the square bracket means include the lower limit, and the round bracket means um, the round bracket here would mean up to but not including. So the cut point is actually cutting off at that upper limit. So if there is a value of 1.5, it would go into this bin. But a value of 2 would have to go into the next bin. So we're trying to accommodate for the decimal places of accuracy with these cut points. All right, after that, it's the same logic as before. So I have 1.5 to under 2. I'm being told there's one value that fits in this bin, and that is 1.8. Then I have, for example, 2 to under 2.5. There are 5 values here, so that would be 2.08, 2.27, 2.42, 2.07, and 2.13. So it's very, very similar to limit grouping. It's just that the cut point means not including. So we're cutting off right before that point. And this is the approach that you're asked to use on the first assignment in the second question. Right? Now, in that particular instance, there's some nuance because they're whole number values, but you would just define the upper point as being a cut point, meaning if you're at the cut point, you move to the next bin. But again, you can see that once we have established the bins, the process here is exactly the same. So regardless of the variable that you were working with, or regardless of the data type that you were working with, the first step in a lot of cases is to find these frequency or relative frequency or percentage distributions. And the way that we do that is by determining the bin. So is it going to be a value from the data set, which in the qualitative case it will be. Okay. Or is it going to be a limit or a cut point group? And that just depends on the amount of repetition at each of the values. So if we have a low amount of repetition and a lot of different values, it's going to be a limit or a cut point grouping illustration. Okay, on slide 17, I summarize those points. So for quantitative data, we have 3 approaches, and how we pick the approach depends on the characteristics of the data. And really what it boils down to in the discrete case is how many unique values do you have? And for the cut point case, typically we use this with decimal places of accuracy, but you can establish cut points with discrete values as well. It's going to produce the same image in the end, or at least it should produce very similar images. Okay, so for qualitative data, we looked at 2 visualization techniques. We had the bar chart and the pie chart. For quantitative data, the 2 visualization techniques that we're going to talk about are the histogram and the boxplot. The histogram is a bar chart, but where the bars are connected. So they're incredibly similar. They're basically constructed the exact same way. It's just that we flush the bars together, whereas in the bar chart, we have separation between the bars. The reason for this is bar charts are used with qualitative data. With qualitative data, you very rarely, if ever, have overlap between the categories, right? So in our illustration, we had A plus, A, and A minus, and then other letter grades, but those are distinct values. So the bars are representing separate outcomes. The histogram, because it's usually established for limit or cut point methods, the bars are connected to represent a flow from each bin into the next. But again, the way that we build these are the bar chart and the histogram are exactly the same. It's just disconnected or connected bars. Okay. All right. Okay, so for our continuous data set that we first looked at a few slides back, we have 22 observations. It's clearly going to be a cut point method because these are continuous values. We've already established the construction of this distribution. Let's take a look at the corresponding histogram. Okay, so for that illustration, we have the following histogram. Now, in this particular case, I drew a frequency histogram, but again, you can make this relative frequency or percentage. The image itself is going to be consistent. It's just what is written on the y-axis. Okay, now the way that this approach would be interpreted is our first bin starts at 1.5. Now notice here that at 2, the lines between the bins are connected. So this is meant to represent that flow that I talked about before. So across the first cut point into the second bin. So again, with histograms, like the only real nuance is that we connect the bars because of this concept of flow of continuous values through the bins. But otherwise, the construction of this is exactly the same as it was for the bar chart. For example, the first bin, which runs from 1.5 to under 2, only had one value. So that's why this bin is at a height of 1. Okay. The second bin, which is from 2 to under 2.5, had a height of 5 because there were 5 observations collected in that bin. Then we have 2 bins with no observations in it, and then 2 more bins with 5 observations. And you can see the same trend. We have nothing between 2.5 and 3.5. And then from 3.5 to 4.5, we have 2 bins at a height of 5 because we have 5 observations in those bins. So the histogram and the bar plot are incredibly similar in how they're constructed. Again, the only difference is this concept of connected or unconnected bars. So with bar charts, we disconnect the bars because they represent unique labels. With histograms, we connect the bars because of the limit or cut point grouping methods that we are considering. All right, so the descriptive part of this. We've established how to construct a histogram, but what can we actually use or say about the histogram? When we want to describe what a histogram is telling us, we are describing what is called the distribution of the data set. And the distribution of the data set is a fancy way of just saying the shape of the data that we have observed. When we want to describe shape, we describe 2 terms, modality and whether the image is skewed or symmetric. The 3 most common shapes are as follows. Okay. Okay. So let the midpoint here in each case be defined as the center. Right? Now this is important. This is important because the center, or having an idea of where the center is what defines the skewness. The most common shape that we will observe looks something like this. Okay, so we have our center, and right at the center, we have a peak. Okay, so in this case, we have a unimodal distribution because there's one peak. And then we have symmetry, or this is symmetric unimodal, because on each side of the peak, or on each side of center, more specifically, you have the same amount of information. Okay, so symmetry means that on each side of center, you have roughly the exact same area underneath this the curve in this case, or underneath the shape that you sketch out. Okay, now this concept is a bit easier to understand in comparison to a skewed object. So common skewed objects will likely look something like this or like this. Now again, in both cases here, we have unimodal distributions. Okay, because there's just one peak. But here we have what we call right or positive skewness. And then here we have the opposing, which is left or negative skewness. Okay. So in comparison these three objects likely will make the most sense. So when we're describing distribution of the data set, we are looking for how many peaks are present in our shape. So here we would have one peak in each of these illustrations. So that makes it unimodal, like unicycle, one. Symmetry means that with respect to center, we have the same area. Right skewness means that the bulk of the area is on the left, but the tail skews to the right or skews positive. So it's actually the direction of the tail that determines the direction of skewness. So in the second illustration, we have, again, right or positive because the tail is pushing in that direction. In the third illustration, we have left or negative because the tail is pushing to the left side or to the negative values. Okay. And the bulk of the observations in this case are on the right. So skewness means that the peak will typically be on one or the other side of center, and then there's going to be this elongated tail that pushes to the left or to the right of that peak. Okay, so we always describe skewness in terms of direction of the skewed tail. Okay, now just for clarity, there are many other possible shapes that histograms can reveal. Like for example, in our illustration, and I have some examples coming up later on as well for the online portion or the extra online portion. Um, for example, we could have something that looks like this. So let's say that center is roughly here in this case. Okay, how would we define this? Well, in this case, we would say that it is bimodal and symmetric, right? So we have two peaks now, bimodal, bicycle. And again, on each side of center, we have roughly the exact same shape or the exact same area. So that's what makes it symmetric, right? And then you could have something, this is going to be a little ridiculous, but just for illustration, let's suppose we had something that looks like this. Right? And then let's say, just for the sake of illustration, the center was right about here. Okay. What would we say about this object? We would say that this is trimodal and right or positive skewed. Okay. You can call right skew positive or left skew negative. Those mean the exact same thing. I typically work with direction when I talk about skewness, so right versus left, but positive versus negative, perfectly acceptable. It just depends on how you want to think about it and how you're comfortable with the definitions. Right and positive mean that the tail is pushing towards the bigger values. Left negative means that the tail is pushing towards lower or negative values. So it's the direction of the tail that we use to describe the skewness. All right, now a little bit later on, there's an illustration where we basically take this concept of sketching and place it on top of a histogram. So there's a few examples that you should refer to. I think it's one of the first online exercises actually. And you would produce your histogram, and then on top of the histogram, you kind of sketch out the curve that would fit on that histogram, and then you describe the shape based off of that value. Okay, so our next set of descriptive measures are actual values, so calculating real numbers. So these obviously are only going to apply in most cases to quantitative data. So if we're going to calculate something, we need to have numeric value that would allow us to do so. The first set of descriptive statistics that we are going to talk about are the measures of center. So the measures of center are typically the mean, the median, and the mode. The mean and the median are only valued or are only applicable in the case of quantitative data. The mode actually works for quantitative and qualitative data. So the mode is the only measure of center that would work for both variable types. Okay. After we discuss the measures of center, we will talk about measures of spread. And then again, in most cases, the measures of spread that we will discuss would only work for quantitative data. Okay, now The first measure of center, which is the mean. The mean is a very commonly used measure of center. It's actually quite easy to calculate. Basically, to find a mean or an average, those are the same thing, you take all of the values in your data set, you add them together, and you divide by the number of values. So for example, in this illustration, we have a data set that gives the stopping distance of 13 cars. So if we want to find the average value for this data set, we simply add the 13 values in the data set together, which you can see here. Okay. And then we divide by the number of data sets or the number of observations, sorry, which you can see here, right? So this is the number of values or observations, and this is this is addition. Okay. So maybe I won't label that one, but and this is addition. So this is the calculation for the mean in all situations. A little bit later, I'm going to show a notation that we use in statistics for the mean and a formula that corresponds to this particular calculation that works across all data sets. But it's important to keep in mind that no matter how complex the formula looks, and it might look a little intimidating at first, the mean is always the addition of all the values divided by the number of values. So in this case, we have a mean of 428 over 13, which is 32.923. So this would give us the average stopping distance of the cars in this data set. So we would say the interpretation of this value, if we had to explain it to someone, we would say that on average, it took 32.923 feet for these 13 cars to come to a stop. So notice that I'm talking strictly about the cars in this data set. So I am using descriptive statistics. I am describing what I have actually seen. Okay, so the next example is the median. So the median is another measure of center. Calculating the median is actually a little bit trickier than you might think because the calculation for the median actually depends on how many observations we have in the data set. So in this illustration, I have the same data set that I just did the average calculation for. So I have a data set with 13 values in it. Now, because 13 is an odd number, okay, so we have an odd number of values. So because 13 is an odd number, the median is actually going to be a point in the data set. So for odd numbered data sets, the median will actually sit on or at an exact point. When we want to find the median, the first thing we have to do is order the values. Typically, smallest to largest is recommended, but you can do largest to smallest and you would get the same result. It's just that later on, having smallest to largest values would be more conducive to the values that we're going to study. Okay, so we have 13 values ordered from smallest to largest. Because it's an odd number data set, we know that the median is going to be an actual point in the data set. So in this case, you can see I've highlighted 32 here. 32 represents the median. Why? Because on each side of 32, we have the same number of values, right? So here, below the median, and here, above the median, I have 6 values, right? I have 6 values, right? So on each side of the median, basically what we're saying is we have the same number of observations. So this is the value that splits the data into 2 equal halves. Now, if we wanted to explain this to someone, we could say something like the same number of cars that took less than 32 feet to come to the stop is equal to the number of cars that took more than 32 feet to come to a stop. So 6 cars took less than the median and 6 cars took more than the median number of feet to come to a stop. That would be one way of explaining this. Okay, now if we have an even number data set, which is what we have here, right? So this is an even numbered data set. The median is actually going to be an average, so we're combining ideas now, of the two center points. So this is an important distinction. So the number of observations dictates where the median is going to be located. So if it's an odd number data set, the median is a middle point in the data. If it's an even number data set, the median sits at the average of the two center points. So in this illustration, I've highlighted the two midpoints, which are 250 and 250, right? So the median in this illustration is actually right here on this line. Okay. And it's the same logic. So this midpoint splits the data into two, this midpoint splits the data into two equally sized halves. Now, in order to calculate the median directly, what we do is we average these two midpoints. So in this case, I have 250 plus 250 is equal to 250. So this here is the median for the data set. Now it worked out to be the exact value because the numbers are the same, but if these values were different, this calculation wouldn't necessarily return 250. Okay. So regardless, if it's even numbered, this is the process we have to take to find the median. Average the center points, so the ordered midpoints. And then we can say something like 50% of the plants had concentrations below 250, 50% had concentrations above 250. So the interpretations of the median are also slightly different depending on the number of values in the data set. Okay, the last example is the mode. The mode is typically the easiest value to find. It's simply the value that occurs the most. Okay, so for example, with data set number 1, there are two modes, 32 and 34, because 32 and 34 both occur twice in the data set. That's more than any other value, so we have two modes. With the second data set, the mode is 250, because 250 occurs 4 times, so the modal number is 250 because it occurs more than any other value. And then the interpretations of these would be exactly in a description of what we had just said. So the mode is describing which value occurs most often. So for example, in this data set, we observed cars that required 32 or 34 feet most often. In the second data set, we observed plants that required 250 milliliters per liter CO2 most often. All right. Now, referring back to our initial description of distribution of the data set, the mean and the median are actually useful values for quantitative data to help us determine the shape. So what do I mean? Let's consider those three main shapes that I had shown before. So let's consider the unimodal symmetric and then the left and right skewed shape. Okay. Okay. All right, so here's my symmetric distribution. This will be my left skew distribution, and this will be my right skew distribution. Okay. All right, now, I probably I could have sketched these a bit better, but a little bit more emphasis on the tail, but let's just say that this is roughly the three shapes. Okay. You can kind of see why this is true based off of the location of the peak. Okay, so the red line is going to dictate center again for all three shapes. So this red line marks center. Okay. Now, in the case of a symmetric distribution, the mean and the median both sit exactly at the center. So if we have a distribution or a data set where we compute mean and median, and they are roughly equal in value, that's an indication of symmetry. Okay, now with the two skew distributions, the median is actually the only value that continues to sit at the center. So this is something unique about the median. It doesn't move with skewness. But the mean, on the other hand, the mean actually gets pulled in the direction of the skewness. So here, for example, the mean is going to be greater than the median. So in the case of a right skewed distribution, the mean gets pulled with the median. In the case of a left skewed distribution, the mean again gets pulled with the skewness. Sorry, I said with the distribution. I meant the mean gets pulled with the skewness. So in the case of a left skew distribution, the mean is going to get pulled towards the lower values, to the negative, to the left. In the case of a right skew distribution, the mean is going to get pulled towards the positive values and to the right. So in general, if we have means and medians, if the mean is greater than the median, this could mean right skew. If the mean is equal to the median, this could mean symmetry. And if the mean is less than the median, this could mean left skew. Okay. So these values, their relationship to one another, give us useful information. So we can actually plot the distribution, we can study the shape of the histogram, and then we can use the mean and the median to reinforce what we think we're observing. So if I think I'm observing a symmetric shape, I should observe roughly equal value of mean and median. If I think I'm observing a skewed shape, then the mean will be bigger than the median in the case of right skewness, which is this way. The mean will be less than the mean in the case of left skewness. Right? So I can use these values in collaboration with the histograms to help reinforce my interpretation of the distribution. But notice that this does nothing for modality. This is strictly just about symmetry versus skewness. All right. Now, this is important. So because, as you will see here, the median is always at the center. That makes it resistant to skewness. So the mean is actually only a good estimate of the center in the case that the distribution is symmetric. Right? But if we have a distribution that we believe to be skewed, the median is the better measure of center. Okay, so this is an important point to keep in mind, especially with respect to the second assignment. The mode is not truly a measure of center in the same way the mean and the median are. And the mode is the only value that actually works for both quantitative and qualitative data. All right. Summation notation. So this is our first formal statistical equation in the course. We use summation notation to describe one of the main measurements of spread, which is called the standard deviation. Now, I introduced summation notation with respect to the mean first because I think it helps with digesting what the formula is telling you. In equation number 1, we have an equation for the mean. Now remember that the mean in all contexts is simply the addition of all of the values in the data set divided by the number of values. That never changes. So the mean is always adding all the values up that you have and dividing by the number of values. So the formula that's shown in equation 1 here is literally communicating that concept. So this leading symbol here, and notice that I'm circling the indices, means add up between the first and the nth value, where n counts the number of observations in the dataset. So this notation that I have circled here means add up. Add up from the first to the last value. Now, the xi there represents a data point. So it's saying add up the data points. So this is actually being applied to the xi. And then it's saying divide by little n. So this is communicating the exact equation that we had verbally discussed for the mean. Add all the values together, divide by n. Let's just look at how it works. Okay, So consider this very simple data set with 5 values in it. We want to compute the sample mean of this data set. How would we do this? Okay, so first we let each of those x values take on a number from the data set. So for example, x1 is the first value in the data set. x1 equals 3.85. x2 is the second value in the data set. x2 is 4.42. x3 is the third value in the data set. x3 is 3.50, etc. Okay, we want to compute the mean. So we're going to use the formula from the previous slide. So the next thing we have to do is add up or follow this instruction here, right? So again, this is saying add from first to nth value. Okay, so this would actually mean, in the context of this data set, add from 1 to 5 the xi. So this literally becomes x1 plus x2 plus x3 plus x4 plus x5, which just turns into the summation of the 5 data points. Okay, so that symbol, again, that funky looking E, as students call it, which is actually capital sigma, is the symbol that we use to designate addition. So add up whatever it is across the bounds. So in this case, just add the 5 values together, gives 18.84. And then we're going to divide by 5, the number of values, the same calculation of the average we talked about before, and that gives us 3.768. All right, so this is summation notation. The summation notation is referring to, again, that funky looking E, as students call it, which means to add together. And the reason we need this is because, first of all, it generalizes across all data sets in a more formal way. But this notation is very helpful for describing standard deviation, which we're going to talk about momentarily. Okay, so we discussed our measures of center, mean, median, mode. Now we're going to talk about measures of spread. So it's good to be able to define average value or roughly where the center is, but we also want to know how the points relate to the center or relate to one another. And that's where the concept of spread comes in. So spread basically means like describe how far or away the points are from center or from one another. There are a number of different like common measures of spread or variation that we can consider. So for example, common ones are the range, which is very easy to compute. The sample standard deviation, very common, but maybe one of the more complex formulas that we will see in the class. Sample variance, this is very easy to compute once you have sample standard deviation. I'll show you how to do this momentarily. And then interquartile range. Also easy to compute, but actually quite informative, whereas the range is not as useful. Okay, so the range, as I had mentioned before, common measure of spread, very easy to find. It is simply the maximum minus the minimum for the data set that you're working with. So if we go back to our data set that had the 13 stopping distances of cars and we wanted to compute the range, we would simply have range is equal to max minus min, which is 60 minus 2, which is 58. All right. So that's it. The range is just the spread or the difference between the largest and the smallest value. And if we wanted to interpret that, we would just say between the highest and the smallest value, there are 58 feet, basically. Okay, now the more complex measures of spread, namely the standard deviation. Okay, so here in equation 3, I have one of 2 formulas that can be used for sample standard deviation. Now notice again that this equation is using the summation notation, which is the same definition that we had just talked about. Okay, so this is saying add from 1 to n. Now in this case, what we are adding is the value xi minus x bar squared. So we are summing across what are called the squared differences with respect to the mean. Then we divide by n minus 1, and then we square root that entire expression. All right, so let's take a look at how this would work. Okay, so for the same data set with 5 observations, first, I'm going to construct a table that allows me to compute the squared differences. So you'll notice that I have a column with observation number, right? And then I have in the second column the values from the data set next to their observation number. So once again, what I am saying here is x1 is 3.85, x2 is 4.42, x3 is 3.5, x4 is 2.07. Now, from our previous illustration, we know that the sample mean is 3.768. So this is what we computed in our last example on summation notation. The first thing I'm going to do on the path to constructing the sample standard deviation is take each value in the data set and subtract the mean. Okay, so for example, this quantity here is 3.85 minus 3.768. Okay, and that's it. So I'm doing that for each value. The second value, for example, would be 4.42 minus 3.768. The third value would be 3.5 minus 3.768, etc. Then I'm squaring each of these quantities. So I have in the third column here, this first value is 0.082 squared. And then here I would have 0.652 squared, etc. Okay, so I have my definitions. X1 is the first value, X2 is the second value, X3 is the third value. I have to compute the sample mean, which we had already done, but in some illustrations you might have to do within the standard deviation question. Then I subtract the mean from each value, third column. Then I square each of those differences, fourth column. Then the last thing I'm going to do is just simply add those 5 values together. So this quantity here, the 4.90466, this is 0.00672 plus 0.42510 plus the rest of the values. So I'm just adding together those 5 squared differences in the fourth column. And that gives me the sum of the squared differences about the mean. Now, the last thing I have to do is just plug into my formula. So I have S is the square root of the sum of those squared differences divided by n minus 1. So I have the square root of the 4.90466 divided by 5 minus 1. That gives me the square root of 1.2617, right? So just again, for clarity, this is 4.90466 divided by 4. And then I'm going to take the square root of that, and I have 1.107, right? And this is how we use the sample standard deviation formula. And again, the sample standard deviation is a very common measure of spread, especially if we are going to use the sample mean as our measure of center. Okay, now there is another way of computing the sample standard deviation, and that's shown in equation 4. So instead of having to find the square differences about the mean, what we can do is just square each of the values, add those together, and then subtract the sum of the values all squared. Okay, so equation 4 and equation 3 give the exact same thing. Okay, so we have two formula, which are called the defining formula in the case of equation 3 and the computing formula in the case of equation 4. They are used to find the same value, which is the sample standard deviation. So let's take a look at this now. Okay, so for the same data set, I'm going to use the computing formula. All right, so from the previous slide, I know my computing formula is the sum of the xi squared minus the sum of the xi all squared over little n. Right, so what I have here is the addition of the 5 values. So if I add those 5 values together, I have 18.84. Then what I'm doing is I'm squaring each of the values in the data set and adding those squared values together. Okay, so this quantity here, for example, is 3.85 squared plus 4.42 squared plus 3.50 squared plus 2.07 squared plus 5.00 squared. Okay, so that second formula, the sum of the xi squared, means square each value and then add the whole thing together. So that would literally be 3.85 squared plus 4.42 squared plus 3.50 squared, etc. Okay, so when I do that, I end up with 75.8938. So you can already see that this is actually a faster way of getting to the end result. So then all I have to do is plug into my formula. So the 75.8938 gets plugged in for the sum of the xi squared. The 18.84 gets plugged in for the sum of the xi. So I have 75.8938 minus 18.84 squared over 5, and that whole thing is divided by 5 minus 1. Okay, so then I do the squared divided by 5 calculation first. So I have 75.8938 minus 70.98912 over 4. Notice that that gives me the exact same quantity from the previous example. So now you can already see that these values are going to agree. So if you want to check your work, you will notice that the sum from I equals 1 to n of xi minus x bar squared is equal to the sum from I equals 1 to n xi squared minus the sum I equals 1 to n xi all squared over n. Okay, so those quantities are going to return the same number. So this is a way for you to validate the calculations when you are doing them by hand, which is the case on the second assignment. All right. Okay. So what does the sample standard deviation measure? It measures how far the observations are from the sample mean. So if we have a really big sample standard deviation, it means that the values are very far from the mean. If we have a really small sample standard deviation, it means that the values are close to the mean. Just like the mean, the standard deviation is heavily influenced by outlying points. So it's not actually ideal to use the mean and the standard deviation in the case of skewness, because a lot of the time outliers can actually are what cause skewness. In some cases, you can have outliers, which we'll talk about in a little bit in more detail, in symmetric shapes, but a lot of the time we observe them in skewed shapes. So the main point that I want to take away here is the mean and the sample standard deviation are a combo, a center measurement and a spread measurement that work together. The mean is influenced by skewness. So therefore, the standard deviation is also going to be influenced by skewness. So it's not as reliable in the case of a skewed distribution. So this is a good tandem in the case of symmetry. I mentioned before that we also have what is called the sample variance, which is another measure of spread. The sample variance is simply the square of the sample standard deviation. So the computation of the variance is identical to the computation of the sample standard deviation. The only difference is that we don't square root. So if you have sample standard deviation, you just square it to get the variance. If you have sample variance, you just square root it to get the deviation. Now, we use the standard deviation more often because it's an easier value to explain. The variance is very difficult to explain, and it doesn't give us a lot of value in the context of any particular data set. The reason being that basically what it is just an average of those squared differences. So the variance is most useful as a tool of comparison with other variances from other data sets. But the deviation has a more natural interpretation in the context of any given data set. Okay, so we know that the mean and the sample standard deviation are a good combo if we have symmetric data. We know that if we have skewed data, the median sits right at the midpoint. So how can we build assessments of spread for skewed distributions? Well, what we can do is use what are called percentiles. The median is actually a percentile. It's the 50th percentile. So our way of assessing spread for skewed data sets is to consider um, a set of percentiles, which are called quartiles, right? More specifically, what we do is we consider what is called the 5-number summary. So the 5-number summary is the minimum value in the data set, the maximum value in the data set, and then the 3 quartiles. So the 25th percentile, the 50th percentile, which is the median, and the 3rd quartile. From the min and the max, we can compute the range, and from the 3rd and the 1st quartile, we can compute the interquartile range, or the IQR. So in summary, when we are working with data sets that we believe to be skewed and we want to define center and spread, we use a set of percentiles. So markers of the data set that define how much information is on each side of them. Specifically, we use what would be like the 0 percentile, the 25th, the 50th, and the 75th percentile, and then like the 100th percentile, essentially. And this is our 5-number summary. Okay, so let's compute the 5-number summary for this data set below. Now, you'll notice that this data set is already ordered for us. And we have, in this particular data set, 9 values. All right, now we want to find the 5-number summary first. So we want the min, we want Q1, we want Q2, we want Q3, and we want the max. So we want to find, okay, sorry, I cut out there for a sec. So again, we're doing an illustration of the 5-number summary for this data set with 9 values. So the first thing we're going to do in all cases is order the values in the data set. Now in this illustration, I already have the values ordered, but if they were not pre-ordered, you would have to put them from smallest to largest yourself. Okay, so the min and the max are very easy to pick off in any given case, right? Like they are obviously just the smallest value in the data set and the largest value in the data set. Now, the next thing that we would do is find the median. So again, the median is the center point. We have an odd numbered data set. So the median for an odd numbered data set is actually going to it's going to be exactly equal to the middle value. So for us, that is value number 5. So the 5th value in this data set is the value that places an equal number of observations on each side of it. So we have 67 in this case as our median, because on each side of 67, we have 4 values. Okay, so the median here is 67. Okay, how do we find Q1 and Q3? Q1 and Q3, you can think of them as the medians of the lower and upper half. Now, in the case of an odd number data set, our calculation for the median, or for Q1, will be the median of 56, 61, 63, 64, and 67. So notice that in this situation where I have an odd number data set, I'm taking the median into my Q1 calculation. So this is the median of 5 values, which is an odd number again. So that means that 63 is going to be Q1. That's the midpoint of the lower half. Okay, similarly, the upper half, Q3 in this case, will be the median of 67, 79, 84, 91, 99, which is 84. Okay, so this again is the midpoint of the upper half. All right, so the IQR for this data set then is Q3 minus Q1, which is 84 minus 63, which is 21. Okay. So for this data set, our 5-number summary is composed of 56, 63, 67, 84, and 99. Our IQR, which is the difference between Q3 and Q1, is equal to 21 because we have 84 minus 63. So we know that 67 therefore is at the center. Now, what we can observe when we look at the values is from 67 or from the center to Q1, we only have a difference of 4. But from Q2 to Q3, we have a difference of 84 minus 67, which would be 17. So there's a bigger spacing between Q2 and Q3 than there is between Q2 and Q1. So that implies skewness. But let's take a closer look at how we can use the 5-number summary to make a statement about the shape. Okay, so our second visualization technique for quantitative data is a box plot. What is a box plot? It's just a graph of the 5-number summary in most cases. Box plots can also be used to detect outlying points in the dataset. And this is done through the construction of what are called limit rules. Now, basically, the way that this works is you compute two limits, a lower limit and an upper limit. That's going to give you value. And then you're going to check to see if there is anything on each side of these limits. So are there any values below the lower limit, any values above the upper limit? In the online exercises that are associated with this lecture set, I have an illustration where I do this construction from scratch. So from the start of a data set, I compute the limits, and then I check for outliers, and you can see how the box plot is constructed in this case. Right now, I just want to show for the data set that we had just considered, or a very similar one anyways, the construction of a box plot. Okay, so in this data set, we have slightly different values, as you can see here. So I've changed a few of the quantities. But what you'll notice is we have a 5-number summary where values are in the same place. So this is going to be the min. This is going to be Q1. This is going to be Q3 or Q2, sorry. This is going to be Q3, and this is going to be the max. And you can prove that using the same strategy that we had just gone through in the previous illustration. Okay, now the box plot, as you can see below, is a set of basically 5 vertical lines at each of these markers, right? So for example, here we have the min, here we have Q1, here we have Q2, here we have Q3, and here we have the max, right? So the box is defining the quartiles, and then those limits in this case are defining the min and the max. Again, please review the online exercise for box plot construction, because in that case, you'll see how the limit moves with the rule. So it's not always the case that the min and the max will be marked exactly on the box plot as shown here. If those points were outliers, we would actually mark the limit and then mark the point with respect to that limit. But as you can see, the box plot here is an indication of the shape of the data strictly with respect to skewness and symmetry. And what it is a sketch of the 5-number summary. Right, so how can we infer shape from this? All right, so box plots can be used in the following way. I'm going to draw these illustrations. I'll do them horizontally, but you can actually draw box plots vertically. It gives you the same information. So let's suppose we have, or actually what I'll do is I'll make one axis here. Sketch this point below. Okay, and then I'm going to have 1, 2, 3. Okay, now let's suppose that we have a box plot that looks like this, for example. Then we have a box plot that looks like this. For example. Sorry about the rough sketch. And then we have a box plot that looks like this, for example. Okay, what you'll notice here in these three kind of like not very good sketches, but is we have different separation between the 5-number summary values. So here in the first illustration, we have a really tight grouping on the lower half of the data. So the minimum Q1 and Q2 are really close together. Then Q3 kind of expands further away from Q2, and then the max is very far away from those values. This is an indication of right skewness. So the points are pushing away in the positive direction. In the second plot, we have roughly equal spacing between each member of the 5-number summary. So this would be symmetry. And then in the last case, we have a really tight grouping in the high values, and then things push away in the lower half. So this would be left skewness. So with box plots, we can again infer the direction of skewness or symmetry, but we can't say anything about modality. And the way that we would infer if they're skewed or symmetric is based off the spacing between the points. So the 5-number summary, its usefulness in terms of spread and shape is in helping us to assess the direction, or the 5-number summary is most useful in helping us determine shape, because we can look at the spacing between each of the values, and then we can use that to determine if it's right, left, or symmetric, or roughly speaking, right, left, or symmetric. So the plot associated with that summary, the box plot, this is how we can describe what we are seeing based off those plots. So once we build the shape out, we can just basically say, like, how close together do the values appear to be? And then we can assess the direction of skewness or the symmetry based off of the relationship of those 5 values. Okay, in summary, when a data set is symmetric, the mean and the deviation are the most common measures of center. When a data set is skewed, we can still use mean and standard deviation, but the results will be somewhat misleading because the mean is not going to actually be at the center, and the deviation is a symmetric measure about center, so it's not going to capture the real relationship among the points. So for skewed data, the median and the 5-number summary and then the associated ranges are most appropriate because they're going to reveal that skewness based off of how close together the values are in that particular summary. All right. The last thing that we have to talk about is an association between two variables. So if we have two quantitative variables and we want to talk about the relation between them, that requires a very specific type of plot, which is called a scatter plot. Now in the online exercises, I have an example that is showing what I mean by a data set with two quantitative variables and what the scatter plot is going to look like and how we describe that. So what I want to do here is just give you an idea of common scatter plot shapes that you can apply to that illustration. Okay, so roughly speaking, or let's say not so roughly speaking, what is a scatter plot? It's a coordinate grid. So we're going to have something that looks like this. We're going to have an X and a Y value for two quantitative measurements. And then on the grid, you might have observations that are set up in this way. So this is showing that the observations follow a straight line pattern. So what we would say here is that the relationship between the points is positive and linear. So we have an increasing trend as X is getting bigger, Y is getting bigger, and the points follow the line, right? Now there are many different relationships that a scatter plot can reveal. So for example, in the first plot, we had positive linearity. We can also have something that goes in the opposite direction. So something like this. Oh, sorry, I got to move my line a little bit. Okay. So what's happening here is we then have what we would describe as a negative linear relationship. Okay. Now, I can also have shapes that are nonlinear but have positive trend, right? So common examples of that might be something like this. Okay, so this has obvious curvature to it. So we can see that if we tried to draw a line through it, it wouldn't fit. The trend here is more like this. So what we have in this case would be positive and non-linear. Okay, and then we can also have relationships that are non-linear and neither positive or negative. So for example, if you had like something that was parabolic, like this, right? So in this case, the shape or the trend is something like that. This would be simply non-linear, but it's not positive or negative because it's a parabolic shape, right? So we would probably be more inclined to say, in that case, parabolic. But the main takeaway here is that we can describe the relationship or the shape between two quantitative variables via a scatter plot. And again, in the online exercises associated with this set, I give a very pointed example of this that I encourage you to review. Okay, so that brings us to the end of this portion of the set. So again, there are exercises that are associated with this set that have accompanying videos that you are meant to work through before the end of the second week. This set covers a lot of information. It's one of the longer sets in the course, actually. But in general, what we have done today is sort of a crash course in descriptive statistics. So we've talked about how to organize data based off of the type, how to visualize data, again, based off of the type, and then common computations or summary statistics like measures of center and measures of spread that are also chosen based off of the type of variable and the relationship between the variables or the shape of the data set. Okay, that's all for now. I hope this was helpful. And if not, please let me know. And I welcome any questions either via office hours or at our first in-person class.